Okay, so we're going to continue learning more about limits. Yesterday we reviewed some basic limit properties, okay? Basically what we did is we recall the importance of the word approaching, okay? If the limit of a function equals the value, we say that the function is continuous at that point. Ideally, we would get a value when we substitute any number into a function, like yesterday. For example, if you have that your function is f of x is equal to sine of x, we can plug any number in the domain into x and get a value of f of x. Let x be 0, what would you get? Well, think about something. So you have f of 0 is going to be equal to sine of 0. What's that? If you remember your unit circle, you know that that's 0. So in this situation, what do you think that it would be the limit when x approaches to 0 of sine of x? And you might think, oh, this is 0, and you are right. Okay? However, as we recall from last year, not every function has an infinite domain. Let's look at the function. Let's complicate this function a little bit more, and let's think of f of x as sine of x divided by x. What would happen if you plug 0? If we plug 0 here, you would have something like this. You would have f of 0 is equal to sine of 0 divided by 0, which you know that it's 0 over 0, which is a big sad face, so no, okay? So that's an indetermination. So we need to look at more. We need to look at the graph of this function, okay? So let's look at the graph of this function over here. So the graph is this one, okay? So this is f, okay? So what can you say about the value as x approaches to 0? Okay, so if we are taking it from the left, when x approaches to 0, we know that it's getting very close to this number that apparently is 1, and if we do it from the right, it's 1. So what can you conclude from this graph? From this graph, we can conclude that the limit when x approaches to 0 of the function sine of x divided by x is going to be equal to 1. So today we will discuss how to solve this kind of problems and other special trig functions algebraically. You will have to get creative. We are too young right now to understand the following three rules, so we'll have that discussion later. So far, we know that this is going to be 1. Okay? Guess what? This one, since you know that the tangent is equal to sine over cosine, so you have that this is going to be equal to the limit of sine of x divided by cosine of x divided by x approaches to 0, you know that this is going to be equal to the limit x approaches to 0, and you can decompose this as sine of x divided by x times 1 over cosine of x. Now you know that this value from this one is 1, okay? And then when you plug 0 to the cosine, you know that you have a 1 over 1, meaning this is also going to be 1. Okay, now another interesting one that you have over here is when you have 1 minus cosine of x. This one, you would have a 0 over 0, but in reality what we have is that this is going to be 0. Okay, in general. Okay, so you do need to remember that tangent x divided by x, when the limit of x approaches to 0 is 1, the limit of x when x approaches to 0 of 1 minus cosine of x divided by x is 0, and then this one that we already talked about. Okay. So another formula that it's important that you remember, that usually, I don't know why books and everything, they don't mention it a lot, is this one. The limit when x approaches to 0 of x divided by sine of x is also equal to 1. Okay? So let's talk about the squeeze theorem. Okay? The squeeze theorem tells you that if you have a function h of x that it's less or equal than f of x, then it's less or equal than g of x for all x in an open interval containing c, except possibly at c itself. And if you have that the limits of these three functions when x approaches to c are equal, the extremes are equal, then the one in the middle is going to be exactly the same value of the other two. You are going to ask me, when are we going to use this? Well, when you don't have enough information of this one, but you have enough information from the sideways, it's when you are going to use this kind of theorem, and that's why we call it the squeeze theorem, okay? Because we're sandwiching the equation in the middle, okay? So let's look at this example, okay? So we have that if 2 is less or equal than f of x, less or equal than x squared plus 2 for all x, they are asking you to find the limit when x approaches to 0 of f of x. So what are you going to do? You are going to compute the limits of each of the pieces, okay? So it's pretty similar to what you were doing back in algebra 1 and 2 when you were doing inequalities, okay? So you are going to apply the limit when x approaches to 0 to all the sides of your inequality. Okay, so you have something that looks like this. Now, whenever you're looking at this situation, you realize, hey, it's pretty simple to find the limit of this one. Why? What is the limit when x approaches to 0 of 2? You know that that one is going to be 2, which is going to be less than, and we cannot compute this because we don't have enough information of the f of x. But you know that it's going to be less or equal, and then you can compute this one. When you put the 0 here, you know that this is going to be a 0 plus 2, meaning that you have that this is going to be equal to 2. Thus, okay, by squeeze theorem, we know that the limit when x approaches to 0 of the function f of x is going to be equal to 2. Please remember that when you are using a theorem, you do need to state it, okay? It's quite important.